for the nice introduction. And I'm happy to wake up early. Actually a late riser. So today when I woke up at 5:30 in the morning, I felt so good that, okay, so I should change my habit. Like it's waking up early really feels much better. Okay. So I'm going to talk about efficient fine-grained algorithms. So here probably the term fine-grained probably requires a little bit of introductions, but by now it's also quite well understood what fine-grained means. It really means like understanding efficiency at the finest possible level. So in tradition, okay. So in traditional complexity theory, generally the problems that you can solve in polynomial time are called efficient, whereas the problems that are NP-hard, they are like inefficient. But this crude distinction of efficiency polynomial versus NP-hard, this is obviously not sufficient especially when we are dealing with large data sets. There we really want to understand whether you can design an algorithm that runs in, say, n cube time versus n square time, where n is the length of the input into the 1.5 and so on. So we want to understand these fine-grained details about the time complexity of a particular problem. Here is in the yellow that you can see in the slide is an extract from a monologue by Scott Aronson, where he said, of course, like that's what we want to understand. But given the current status of complexity theory, where we do not even understand whether P equals NP or not, we are very far away from understanding whether distinguishing these complexity classes of n squared versus linear versus n cube and so on. In order to overcome this barrier, what the researchers have done in the last 2 decades, like they have come up with stronger conjectures. For example, instead of saying that satisfiability is NP-hard, like you can think about strong ETH, which is saying the exhaustive enumeration is probably the best algorithm for solving SAT. So even you cannot get an algorithm that runs in, say, 1.99 to the power n, where n is the number of variables, for solving satisfiability. Or you can think about APSP hardness, which is saying that if you have a graph with n nodes and the graph is dense, and so you can obviously compute all Pei-Shorter's path in order of n cube time and assume that's the best possible. Okay, so that's the APSP conjecture and so on. So when you have these stronger conjectures, using these you can classify problems into different classes. So previously, the problems in polynomial time, they used to look something like this. There were many important problems. We were always interested in running time, but we really didn't understand any connections between them. And then by the work of many researchers, some of them are present in the audience here. Now the class P looks like this, where we do understand relationships between problems. For example, like if we cannot solve satisfiability in so if you're assuming strong ETH, like we cannot have faster algorithm for, say, edit distance, which requires n squared time to solve it exactly, and it's saying you cannot break this n squared running time if you assume strong ETH. So it's a very strange connection between the running time of an NP-hard problem to low polynomial time complexity problems. And similarly, if you assume APSP hardness, like you can show many problems in graphs and matrices, they are equivalent to each other and they are all cubic hard. So this kind of relationships emerged because of the work in fine-grained complexity. And generally, like research in theory, they do not make into the news, but some of these problems, some of these results become so popular that they even made it to the media, like the edit distance results, like which says a strong ETH refuting, you cannot get better algorithms unless you refute strong ETH, which is all good. But then obviously, like with great works, like sometimes comes great criticism. It's not great criticism, but there was some criticism, which where there was a biologist who was in Berkeley before, and now he has moved to Caltech. Like he claimed in his blog, like, hey, these lower bounds, they basically do not apply in practice where we are solving, say, edit distance problems, sequence similarity problems in biology without much difficulties. If its running time were really n squared and n is huge in this context in biology, then obviously there would have been much more like stronger difficulties in practice, which he didn't. He claimed that doesn't arise. Anyway, so he put some reasoning behind that. I'm not going into that, but the takeaway from here is like even if there are strong lower bounds, you should not feel too negative about it. There are way around. One is like you can look at the structural. In practical instances, there might be more practical instances may be much more structured. So you can use those to develop better algorithms and break the lower bounds. Or the other way is like to allow some suboptimality where you are not looking for the optimal solution, but close to optimal. And when you allow this kind of approximations, most of these lower bounds will break down. So that's kind of the regime of fine-grained approximation, which I'm going to focus in this talk. Obviously, approximation algorithms, it has a long, rich history. For NP-hard problems, there had been a long line of work, right, in approximation algorithms to develop polynomial time faster algorithm for NP-hard problems, allowing approximation. So here what we are saying that we have polynomial time problems already, but we want to break the whatever is n square or n cube, whatever those barriers, using allowing approximations. And for that, naturally the tools that we would need is going to differ quite significantly from the tools that we know from the theory from approximation algorithms for NP-hard problems, because there the focus is to get the running time down to polynomial time. And here we are really looking at low polynomial time and trying to design faster algorithms and understand the trade-offs. The kind of results that we have got in this fine-grained approximation area in the last few years, like we have a lot of results in that area. Like for example, for string edit distance, you can. I don't think I need to introduce string edit distance, what the problem is, but I will still do that just in case. Like in string edit distance, you have two strings, the reference string and the input string. And you want to make minimum edits on the input string, insertion, deletion, and substitution of characters, so that after the edits, the input string looks like the reference string. For example, here, like if you delete this capital T, then you substitute this A with a C, and then you insert T at the end. Then with these three edits, you can convert this input string into the reference string. And as I said, the string edit distance, like you can design an n-square algorithm using dynamic programming. And that's kind of what you can do if you're considering optimum solutions, unless if you believe in strong ETH. But if you allow approximations, there have been a lot of progress in devising faster algorithms for string edit distance, allowing approximations. So a couple of years back in Fox 2018, Chakravarti, Das, Goldenberg, Kauki, and Sachs, they gave an algorithm that runs in sub-quadratic time and gets a constant factor approximation for edit distance. And very recently, just a month back or 2 months back, like we got another breakthrough here where Alex Andoni and one of his students, they got a near linear time algorithm for edit distance, getting constant factor approximation. And we have some results where we can go in sublinear time, obviously with OS approximation ratio. So there is all these trade-offs that we have got for edit distance, allowing approximations. For Alpert-Curtis path, again, that's the basis for cubic hardness. If you allow approximation, you can do much better. And some of these algorithms that are not really restricted to Alpert-Curtis path, but can be applied to even pretty different looking problems, which were all cubic time, kind of, there were no algorithms that you can do that runs better than cubic time, but you can allow approximation and break that hardness. And again, there are problems related to edit distance, for which there were like n cube running time. So for APSP and the class of problems that like stochastic grammar parsing and some other problems in this slide, you can break n cube. You can go down to running time that matches fast matrix multiplication. For some other problems, you can even go down much, like from n cube to you can go down to near linear using allowing approximations. RNA folding, this is another problem, which is a very basic problem in computational biology. Since 1980 till maybe 2016, there was only an n-cube time algorithm for solving RNA folding, but now we know like how to get better running time, even for the exact problem of RNA folding. And if we allow approximation, we can run it even faster. Okay, so these are just some examples of very basic problems that for which allowing approximations, we have seen quite a bit of progress. So now the question is, if we are trying to design approximation algorithms for polynomial time problems, it would be good to have some generic tools that we can apply, not just to a specific problem, but to a class of problems. The question is like, what kind of tools they would be? Well, if you look at these examples like edit distance or Alpia-Shortest path or RNA folding, how do you solve them exactly? Like for all of these, you are basically using a dynamic programming. So if you can have some tools like these dynamic programmings, they often suffer from high time complexity, high space complexity. So if you can have some way of taking a dynamic programming and massaging it so that it has a better running time, better space complexity, then you can apply it much more generically to have faster algorithms for these polynomial time problems. So that's kind of what we are trying to do. So we considered dynamic programming and tried to do two things. So one is to map a dynamic programming solution into computing fast matrix multiplication. And the other is, in dynamic programming, we maintain some steps, right? And so what we did, we call it like amnesic or forgetful dynamic programming, where we try to forget some of these steps in a systematic way. So we do not maintain all the steps of dynamic programming, and we do so in a more systematic way so that we can improve on the time and space complexity and at the cost of approximation, but we have improvements. So I'm going to show you these two flavors of taking dynamic programming and either to convert into computing matrix multiplications or to use this amnesic dynamic programming using this problem of language edit distance. Okay? So any questions so far? Okay, if everything is good, so let me just describe what this language edit distance problem is, because I'm bringing in another new problem, and I have already talked about many different example problems so far. So just let me tell you that this is a very generic problem that is very interconnected to the problems that I have described, like RNA folding, APSP, even edit distance, and so on. Okay, so what is language edit distance? It generalizes two very basic problems. One is context-free grammar recognition. In context-free grammar recognition, you are given a string, you are given a sequence, and you are given a grammar. You want to know whether this sequence can be parsed according to this. These are the rules of the grammar. That's context-free grammar recognition. And the other is string edit distance, which I already explained, that you have two strings and you want to make minimum edits on them to make them look alike. So you have one reference string and one input string. Now, language edit distance, it generalizes both these problems. So instead of having one string as your reference string, here you will have a set of reference strings. And now you are given this input string, and you want to make minimum edits on this input string so that it looks like at least one of these reference strings. So instead of one, you have a set. So in this way, it generalizes string edit distance. And this set is not any arbitrary set. This is generated from all these sequences here are part of a context-free language. Okay. So in context-free grammar recognition, we basically are asking whether this input string belongs to this set, that is whether the edit distance is 0 or non-zero. And here we want to compute the distance. So in this way, language edit distance is generalized as context-free grammar recognition. This problem has a old history. Like it was studied back in 1972 by Yahoo and Peterson, where they gave an algorithm, again using dynamic programming, that runs in order of n cubed time. N is the length of the sequence with quadratic dependency on the grammar size. And that quadratic dependency on the grammar size was later improved by Gene Myers in 1995. But the cubic time, the cubic dependency, it stayed. And this problem, it has a lot of applications because it tries to answer questions of the following form, that when you are given a model which is specified by a formal language, does your data fit the model? So your formal language is suppose your context-free language, and you have the data. You are asking whether the data fits the model or what changes are required in your data to make it fit the model. And this question appears in many different applications, like in databases for data quality management, in compilers for designing error correcting parsers. The RNA folding that I mentioned could be seen as a special case of language edit distance in natural language processing, where you want to correct grammatical mistakes and so on. So it has many applications. So naturally, n cube time is not desirable. So there were papers which tried to come up with local greedy algorithms, but they were all heuristics, and there was no performance guarantees on those algorithms. So I will take this language edit distance, and I will show you how we can improve the cubic running time using these two different ways of, one, converting a dynamic programming to solving matrix multiplications over some special algebraic structures, and the other is doing MSIC dynamic programming. So let's look at the dynamic programming for language edit distance. So the dynamic programming for language edit distance goes like as follows. The rules here, which are written in white, these are the original rules of the grammar. Now you add some extra rules to this grammar. Okay, so here in the original grammar, this non-terminal capital R was producing this symbol A. Now you let this non-terminal capital R to produce the symbol B as well. So basically we are allowing substitution. In the original grammar, R could have produced only A, but now we are letting it produce B. So we are allowing substitution. And if we are allowing substitution, we have to pay for it. So we associate this rule with a score of 1. Similarly, in the original grammar, capital L was producing the symbol B, but now we let capital L to produce the symbol A as well. So we are again allowing substitution. So we have to pay for it. So we add a score of 1. Similarly, you can add this error producing rules for insertions and for deletions. Now, once you add the original rules of the grammar, they will have a cost of 0. And these other rules, this error producing rules for substitutions, for insertions and deletions, they will have a corresponding scores. Now, once you have this code grammar, you are given the input string and you want to find a parsing of the input string with minimum total cost or minimum total score. Okay, so that's your language edit distance problem now becomes like compute the parsing with minimum total cost. And how can you do that? If you're looking for if you're looking at the substring I to j, then and suppose this I to k minus 1, the substring I to k minus 1 can be parsed starting from this non-terminal capital A with a cost of x, and the substring k to j can be parsed from non-terminal capital B with a cost of y. Then if there is a production which says A and B can be combined to get the non-terminal C, then we can get ij by combining A and B, we get C. And what will be the score? The score will be just x plus y. And if we have multiple x's here, x1, x2 to xi, and multiple y's here, y1, y2, and so on, then what will be your z? It will be the minimum of x1 plus y1, x2 plus y2, and so on. So it will be the mean plus, okay? And now what is the running time? You have to fill up this n squared size table. To fill up each entry, you have to look at all these breakpoints, right? I plus 1, I plus 2, I plus 3, up to j minus 1. So order of n in the worst case. Therefore, to fill up every entry, you will require order of n time, and you have to fill up n square size table. So overall, it will give you an order of n cube algorithm. Now let's try to view this dynamic programming computation in a different way. So using matrix multiplication. Okay, so this is how we are going to define the matrix multiplication here. It's so if you are given this matrix, if the matrix entries will be octuples of this following form, that it will have a non-terminal and it will have a score. And when you are multiplying, if ik has a to x, a and x, and kj has b and y, and if there is a production that says that a and b can be combined to get c, then when you are multiplying, from a, b, you will get c, and from x and y, you will get x plus y. And if there are multiple such entries like ax1, ax2, and by1, by2, what you will be getting is the mean plus of this x1 plus y, y1, x2 plus y2, and so on. So it can be shown if you start with just the diagonal entries in this matrix, which you can fill in manually, and then you keep on doing this matrix multiplication and you compute the transitive closure, then at the end, the entries of the transitive closure will be exactly same as what you would get using the dynamic programming, okay? So this is an alternative way of viewing the dynamic programming process using the special type of matrix multiplication. Now the question is whether this viewpoint helps to get a faster algorithm. If it has to help, we have to answer two questions here. So one is like whether it's possible to compute each of this matrix product first, and the other is computing the transitive closure first. Let's look at computing the matrix product. I was trying to emphasize that when you're computing this special kind of matrix product, the main operation that you are doing is this mean plus. So basically it can be shown that computing even this special kind of matrix product is equivalent in running time to computing mean plus product. What is mean plus product? So in mean plus product, if C is your product matrix and you want to compute Cij, the ijth entry, then you will look at all the k's and you will be taking aik plus bkj and the minimum over the k. Okay, so in normal matrix multiplication, this plus will be multiplication and this mean will be addition. So here we are replacing addition with mean and the multiplication with plus, so mean plus. But unlike normal matrix multiplication, mean plus product, we do not know any faster algorithm for it than NQ. And in fact, mean plus product computation is equivalent in time complexity to all-pair shortest path. So if you believe in the all-pair shortest path conjecture, then there is really no faster algorithm for mean plus product. So that doesn't directly help us, but the good news is there are faster approximation algorithms for mean plus product. So there is an algorithm by Uri Zwick from 1998, where you can get much faster algorithm for mean plus product. In fact, that will run in time. Running time will be same as fast matrix multiplication. So maybe we can use that because we are trying to do approximation. Maybe we can use Zwick's algorithm to make it run faster. So that's the matrix product part. Now the transitive closure part. Generally computing transitive closure is easy because there you start with a matrix A, you compute A squared, then A to the 4 and so on. So you just do log n computations and with an overhead of log n, which you often can even avoid, you will get you will compute the transitive closure. So the running time of the transitive closure will be same as the running time of the single matrix product in general situation. But here, this matrix product is very strange. So this product is neither commutative nor associative. So not having this associative property is very, makes our life much difficult. So for example, here, like if we are trying to multiply these two matrices, so from A and B, suppose you create, so there is a production that combines A and B and gets you C. And maybe there is another matrix here, which has an entry D here. And there is suppose a production that combines C and D. So you can compute the matrix multiplication in this way. But if you try to multiply this matrix that has this entry B with this another matrix that has this entry capital G, but suppose there is no production that combines capital B and B. Okay, so that shows that this particular type of matrix product is not associative, which means you have to compute if you have to compute the transitive closure, you have to multiply these matrices in a very stringent way. And if your parse tree looks, if you have a long parse tree or long recursion, then you might have to multiply the matrices n times in a row, which means the computing transitive closure might take much longer time. And second, like even if you have a very good approximation algorithm, so even if Zwick's algorithm is very good, like this error will be propagating n times and it will not be useful. The question is, what can we do about it? Here comes a very nice result by Leslie Valiant from his PhD thesis back in 1978, where he showed that even when you have this kind of non-associative matrix products, you can still compute the transitive closure in time, same as computing one matrix product by decomposing the matrix in some overlapping submatrices. So generally, when you do divide and conquer, you will break the problems into non-overlapping subinstances. But here, the main idea is that you have to break it into overlapping subinstances and do a divide and conquer, and you can show that you can still compute the transitive closure in time, which is same as computing one matrix product. We can take Leslie Valiant's algorithm and can modify it suitably for our need, and we can solve the transitive closure, in fact, as fast as single matrix product. So that's pretty good. But even then, it's possible that you will be multiplying like pretty large matrices. For example, matrices of dimension into the 1 minus epsilon into the 3 epsilon times. And then each time, if you have a good approximation algorithm, if you use Zwick's algorithm specifically, then the error will propagate, and the best approximation that you're hoping for here will be like n to the epsilon. So we want to do much better. We in fact want to get an approximation like 1 plus epsilon approximation. So if we have to do that, we need more ideas on top of using Valiant's algorithm. So how do we do it? So first of all, an observation. So this is an old result by Alan Gullin and Margalit, wherein they showed that if you are computing mean plus product, then if your matrix entries are not too large, if they're bounded by capital R, then you can solve the mean plus product in time order of R times n to the omega. Omega is the exponent of first matrix multiplication. So you can get much faster algorithm. So here, like, what is the corresponding thing for R here is the edit scores that you are keeping. So you're keeping A, X, B, Y, and so on, right? So these X and Y. So these are the edit distance that you have computed for some substrings. And there is no guarantee that this X and Y will be small. So R is not small here when we are computing mean plus product. But then here comes another observation that when you are computing this mean plus product, if you do not have, if your scores may be, if your entries may be large, but if you do not have too many distinct entries in a particular row or particular column, then you can still compute matrix product fast. So suppose there are capital R distinct entries, distinct scores, then from that you can create numbers in range 1 to R square, and you can map these different scores into this range of 1 to R square, which is known as Sidon sequences, so that each distinct when you look at any pair, their sums will be distinct. So from that, you can basically recover what was the original entry. And then once you have done this mapping, you can employ the algorithm by Alan Gullin and Margalit, because all the entries are now bounded from 1 to R square, and get an algorithm that runs in time R square times n to the omega. Okay, so we can even compute mean plus product fast when there are not too many distinct entries. So now if you look at our computation, so these R corresponds to the scores. So what we need to do in order to employ this second trick is like we need to round the scores so that there are not too many distinct scores. How do you do this rounding? And we have to do the rounding in a way so that the error remains bounded even when we are computing the matrices, like multiplying these matrices say into the epsilon times. So what we do for this, we employ a randomized rounding in the following way. Like if your score y is say 1 plus delta to the r plus k, then we either round it up to 1 plus delta to the power r plus 1, or we round it down to 1 plus delta to the r with appropriate probability. So that on expectation, the score of y remains same as the original score. So this type of rounding is like has a flavor of dependent rounding, which has been used quite successfully for rounding LPs, linear programs, in tackling NP-hard problems to design approximation algorithms. So we borrow the ideas from there and bring it here. That using this kind of dependent randomized rounding, you can basically, you are maintaining the score on expectation, but not only that, you can also show that the variance remains bounded. Even when you are multiplying, suppose you have a long parse tree, you are multiplying the matrices into the epsilon times, but even then, the variance remains bounded. So you can apply concentration inequalities like Chebyshev inequality and show good approximation bounds. So in fact, we get a 1 plus epsilon approximation with high probability. And this kind of techniques of using dependent rounding, you can also use for devising approximation algorithms for a PSP. And if you can design approximation for algorithms for a PSP, obviously you can design approximation algorithms for many other graph and matrix problems. Okay, so this was one way that you can take a dynamic programming problem, convert it into matrix multiplication, even though the matrix multiplication might look pretty strange. It's over a pretty different algebraic structure, but you can utilize that and still design faster algorithms. So one question you might ask here, like why approximation? When we are doing approximation, we have to give some kind of reasoning that why approximation is needed. So we tried to prove lower bounds for language edit distance. And what happened? We could show lower bounds if we only allow insertion as edit operation. We can show that language edit distance and all-pair shortest path, they are equivalent. So if you believe in all-pair shortest path conjecture, it's unlikely that language edit distance will have a running time better than n cubed, so you do need approximation. But when I was trying to design lower bounds allowing insertion, deletion, and substitutions, I miserably failed. And then we started thinking like what's happening, and we basically discovered when you have all these different types of edits, insertion, deletion, and substitutions, then the underlying, where is the difficulty of having this n-cube barrier in language edit distances, unlike underlying mean plus products. So when you have this insertion, deletions, and substitutions, your underlying mean plus product matrices tend to have very nice structures. So if you look at the scores in adjacent rows or adjacent columns, you can show that this difference in the scores is bounded. In fact, their difference could be at most 1. So what does the score represent? Score basically represents like what is the edit distance for a particular substring ij. So now if you're looking at edit distance for a particular substring ij and ij plus 1, how much their difference could be? It could be at most 1. Okay, so that's the intuition why this matrix has this bounded difference property, but this property doesn't hold if you only allow insertion. And that's why when we are allowing insertion, we could show lower bounds, but when we are allowing all the different types of edits, we were not able to show lower bounds. So in a follow-up work, we basically came up with an exact algorithm for mean plus product when the underlying mean plus product matrices have this bounded difference property, and using that, we even got exact algorithm for language edit distance in sub-cubic time. Still, there was a big gap. So here the running time was like n to the 2.82, something like that. And our previous algorithm, the approximation algorithm that I described, had a running time of equivalent to first matrix multiplication, so n to the omega. So there is still a big gap. But so far, the lower bound for language edit distance, allowing insertion, deletion, and substitution, is still n to the omega. So this is a big open question here, like to understand either to have a stronger lower bounds that is higher than n to the omega, or to devise better exact algorithms. So for approximation algorithms, it cannot go beyond below n to the omega, allowing multiplicative approximations. So there you can show examples that n to the omega is kind of the type if you are looking for 1 plus epsilon, if you are looking for any multiplicative approximation. Okay. Oh, and yes, like using our algorithm, when we can not only design an exact algorithm for language edit distance using the exact mean plus product for bounded difference matrices, we also got exact algorithms for RNA folding. It's not surprising because, as I had mentioned before, RNA folding is kind of a special case for language edit distance. So if you have a good algorithm for language edit distance, likely you will have a good algorithm for RNA folding. And also for certain like quadratic problems, you can get faster algorithms. Okay, so now is the time to move to the second line of amnesic dynamic programming. So before we do so, here in this approach, we are taking a dynamic programming and we are converting into computing matrix multiplications, and we are using fast matrix multiplication. So here there is a question like, it can arise that fast matrix multiplication is not so practical. Hence, maybe these algorithms are not so practical. And we might be interested to design algorithms that are purely combinatorial. If you're kind of that kind of person who really wants to design practical algorithms, then maybe this amnesic dynamic programming is for you. So here is basically the concept is very simple. You take dynamic programming. In dynamic programming, we're basically maintaining a table with states. Now in amnesic dynamic programming, you won't maintain all the states. You might just not compute some of the entries in your table. Or what you can do is when you are computing a particular entry, you have to look at the entries that you have computed for the smaller instances. So instead of looking at all the smaller instances that you would generally look at, you will just look at a sample of these entries. Okay. And obviously, this way you can improve the time complexity and space complexity of dynamic programming. But the question is, does it give a good approximation? And for that, obviously, we have to do this selection. If we are just looking at this process where we are computing all the entries of the dynamic programming, but we are not looking at the subproblems, we're just sampling from the subproblems. We have to find a good way of sampling so that we can also guarantee approximation guarantees. Let me tell you what kind of results we get using amnesic dynamic programming. Like for language edit distance from NQ, we can reduce the time complexity to n squared over epsilon with an additive approximation of epsilon n. So if you set your epsilon to be, say, 1 over square root of n, then the running time will be n to the 2.5, and you will get square root of n additive approximation. Similarly for RNA folding. And this amnesic dynamic programming actually helps a lot in reducing the space complexity. So for all these problems using these approaches, you can get a space complexity that is sublinear in n. Whereas if you're looking at the dynamic programming, or if you're looking at like converting dynamic programming to matrix multiplication, for all of these, the space complexity was basically n squared. So here you can reduce the space complexity drastically to sublinear in n. And it also has some other advantages, like dynamic programming is generally a very sequential process. But here, because you are forgetting states and so on, you basically can make it much more like friendly to parallel computation or streaming computation. So all these advantages are there in addition to saving time and space for dynamic programming. Okay, so now let me tell you how you can do it for this language edit distance problem, and that will give you a generic idea how to do it in general. So again, we call the dynamic programming. What we did, like for every substring I to j, we looked at all breakpoints, right? I plus 1, I plus 2, I plus 3 to j minus 1. So we looked at all these order and breakpoints. Now, instead of looking at this order and breakpoints, what we are going to do, we look at, say, log n breakpoints. And then obviously the time complexity will reduce from n cubed to n square log n. So the question is, how do I sample these log n breakpoints from these n breakpoints? The very first thought might be like, I will just sample uniformly at random. Well, that's a very bad choice. Like if you do uniform random sampling from your breakpoints, you will get a terrible approximation guarantees, like order n approximation bounds. Even doesn't matter whether you have a nice fat purse tree or whether it's long and thin. So you will get a bad approximation. So the other idea might be like, if I'm looking at these kind of balanced sparse tree, you see the problems that you're solving at the end. There are many of them, and they are really small. Like they're on over small subinstances. Like the substrings are small. So might be we should really sample aggressively when the instances that we are solving are small length, and we sample much fewer like when we are solving large problems. So then we'll have small errors for small problems, and we'll have large errors for large problems. If you do that, you can handle the situation where your recursion is kind of balanced. So you have a balanced burst tree, because indeed that there will only be too many long problems that you need to solve. And for them, even if you're making large errors, still it should be okay because you're solving your small problems much more accurately. So that's a good thing. But if you have a long and thin kind of burst tree, then you will have as many large problems as small problems. And there your approximation guarantees will again be bad. So what can we do that? So this is the final thing that we do. Basically, for every substring, we sample non-uniformly, and we sample much more aggressively towards the end, and our sampling rate decreases as we go in the middle. Okay, more specifically, this is what we do. So starting from J, we create intervals. So K is a parameter. It will be like 1 over epsilon. So you take intervals of length K, length 2K, length 4K, length 8K, and so on. On the first interval of length K, you sample everything, all the breakpoints. In the second interval of length 2K, you sample the breakpoints with probability half. In the next one, you sample with probability 1/4. And the next one, you sample the probability with probability 1/8, and so on. And similarly, you do it starting from I. Again, you break into intervals of length K, 2K, 4K, 8K, and so on. In the first interval of length K, you sample everything, and then progressively the sampling rate decreases, half, 1/4, 1/8, and so on. So this is how the sampling probability will look like, very high at the end, and it decreases in the middle, okay? And this kind of works out. And in fact, like this will be the, if you look at the sampling probability, the distribution will look something like this for language edit distance. For RNA folding, you can also have a similar algorithm for longest increasing subsequence. That's a one-dimensional problem where you will have a probability distribution like this. And from here, you can think about even higher dimensional dynamic programming, and you can think about what kind of probability distribution you really is looking for. If you have to employ amnestic dynamic programming, it will be something very, like you will be sampling much more aggressively towards the end. And as you're going in the middle, as you're going to the center, the sampling probability will decrease. So why does this approach help? First of all, if you look at short recursion trees, you have many small problems, like many short subinstances. And because you're sampling very aggressively towards the end, you will be sampling very aggressively here, here, and here, right? So for all these subproblems, you're not going to make much mistakes. So that kind of helps in handling short recursion trees. Now, if you look at long recursion trees, look at how these, how did you create this kind of long branching? Because at every time when you're creating a long subproblem, you're also creating a small subproblem. So that means your breakpoint is kind of towards the end. And this is exactly where you are sampling very aggressively. So it's likely you will be sampling this breakpoint or something very close by. And once you do so, your error will be bounded, error will be small. So even for this kind of long recursion trees, if you're sampling using our ideas, like where you're sampling aggressively towards the end and much lower in the middle, you can show that the error remains small even for this long recursion trees. So that's kind of the intuition. And then obviously, if we have mix of long and short and whatever, that proof works out. Okay, and that gives you a generic idea of how you would be doing it even for higher dimensional dynamic programming. And this particular amnesic dynamic programming is not just for language edit distance. You can take any other problems that has this bounded difference property. So the bounded difference property would go as follows, that if you do not change your input instance substantially, your output should not change substantially. So this Lipschitz property, if you have in your problem this Lipschitz property, is very likely that you can take this amnesic dynamic programming approach and it will extend. Okay, so that's the two main things that I wanted to talk about today. There are obviously many open questions. For example, like all the problems so far that have been that I talked about, these are all like for cubic dynamic programming. The question is, what can we do for quadratic dynamic programming? It's likely the techniques will be a bit different, or depending on the structures of the dynamic programmings, or what can you do for higher dimensional dynamic programmings. Hardness of approximation is a big open question here. Truly subcubing mean plus product, I think that will break the PSP conjecture, so that's obviously a big open question. Yeah, so that's it. So thank you. Questions?